Yeah, so thank you so much. Thanks for the organizers for having me. I'm going to temporarily remove my microphone a little bit to say a few things about Elisha. So I'll just say that Elisha and I met many years ago when we were both working in the Panama Canal in 1914. Then the war started, and we both left, and somehow we both came into mathematics.
Thank you.
Okay. Yeah, all right. So I will tell you about virtual torsion and homology of three manifolds. So it's going to be sort of an emphasis on real hyperbolic three manifolds. And I will, at some point, give some consequences for arithmetic real hyperbolic manifolds of simplest type. And then I will also tell you why we don't have such good news in the complex hyperbolic case. But we will get there. And all of this is based on joint work with Daniel Groves. Okay. So like I said, I will be mostly based around hyperbolic three manifolds. So if I write hyperbolic space, most likely it will mean real hyperbolic. Okay. So here is my setting throughout this talk. So M is going to be a compact three manifold. Compact, irreducible three manifold with either empty or toroidal boundary. And with at least one hyperbolic piece in its geometric decomposition. So I'll remind you what this means. You can also say it has positive simplicial volume, but I'll just remind you the geometrization theorem. So let me just say it here. Geometrization theorem. And I apologize if some of you might use a Z and some of you might use an S here. Let me just do that. Geometrization. So this is the geometrization theorem that's due. Sorry, what? So I guess versions of it are due to Thurston, and it was completely resolved by Perelman. So I'll remind you what this means, and it says that if you start with M, a compact irreducible three manifold, you can again say with empty or toroidal boundary, then M can be canonically decomposed I guess into what I'll call, I guess, geometric pieces. And these are pieces which uniquely admit one of the 8 Thurston geometries. So they're modeled on these 8. So I'll remind you what they are. There's S3, E3, this is Euclidean. There's H3, this is our favorite one. Here's the star. There is H2 cross R, S2 cross R, nil, sol, and the universal cover of SL2R. Okay? So again, there's many ways, many reasons why, in some sense, H3 is sort of the most interesting one. Okay. So in this setting, we have our three manifold. It can be canonically decomposed into its geometric pieces, and I want at least one of the pieces to be hyperbolic. And if you want to, you can just think about a hyperbolic 3-manifold. I'm sure you have a favorite one. And if you don't, maybe you should think about the figure 8 knot complement. I think that's one that perhaps many of us in this room like, or at least it's a group or something. Anyways, so that's an example of one. And what else? Oh, maybe I should write that here. Let's do it in a different color. So if you want to think about an example here, take, for example, actually just a hyperbolic 3-manifold of finite volume. And the figure 8 knot complement. I can draw it S3 minus a neighborhood of this. We know that it admits a complete hyperbolic metric, and let me just remind you here of what this group looks like. It has 2 generators. It looks something like this. That might be correct. It might not, but I think that's right. Okay. Oh, and in my notes I wrote it with X and Y, so I don't know if this is correct, but hopefully. Okay. So if you just want an example to think about for the rest of the talk, just think of this one. Okay. Oh, actually something else that I wanted to say. Let me go back here. This manifold, it has a single cusp, which is the neighborhood of this knot that we're removing. And again, let me just remind you that a finite volume hyperbolic manifold, it either has empty boundary or it has toroidal boundary, so it can look something like, here's a little torus. It looks something like that, okay. So having cusps is okay today. Okay. So the goal for today, so I'll say, or I guess not just for today, but it's a good goal in general, is to understand virtual homology of these manifolds. Okay, so I guess earlier today we did see some results that are sort of in this direction, understanding virtual homology, but they were about taking, I guess it's a little different because it was taking sequences of different manifolds, but if you assume, say, that your manifolds all come from a tower of covers, you can say something about the first Betti number, so that is saying something about homology. So that's a general goal. And again, let me just remind you that when I look at it, so I'm always going to stick with first homology with integer coefficients, and this looks something like this. This is the first Betti number, and there is some torsion part. Let's call it T1, okay? So this is torsion part, okay? Oh, let me also tell you that this is first Betti. This is the first Betti number. Okay, and so again, I want to understand virtual homology. And let me just remind you again, if you don't know what virtual means, it just means something that you can say about finite covers. So we do know a lot about how first Betti number grows. So here is a short history lesson. So I guess a consequence of Luke's approximation theorem in this setting is the following. So you start with your manifold M, and you assume, let's say that, let's write it like this. You have some tower of covers. And let's say this is a cofinal tower of regular finite covers. And what Luke says is that whenever you have this, then if you look at the limit as n goes to infinity of the first Betti number for this manifold over, I should have said something. I should have written something else. Let's say these have fundamental groups something like this over the index then this actually converges, and in this case goes to 0, okay? That's the first thing I want to say about that, but I also say something else over here. So again, a consequence of the virtually special theorems, virtually special theorems, and these are due to Agel and Weiss, but in the case of, in this more general setting that they're not always hyperbolic, also, sorry, I won't say this name out loud because I don't think I can. And I also don't know if I can spell it. How do you say this? So I just need to look at my notes. Okay, I hope this is correct. So the virtually special theorems tell us that any of these manifolds have virtually infinite first Betti number. So what that means is that it doesn't matter how large you want your first Betti number to be, you can always find a finite cover with Betti number as large as you want. Okay, so that's what it means to have virtually infinite first Betti number. Okay, so if you look at these two sort of results over here side by side, well, you can always find towers of covers where your first Betti number grows and grows up to infinity. But, well, let's say it's a cofinal tower of regular covers. The limit goes to 0 here, so you have something going off to infinity, but not very fast. Okay, so there is sort of some bound on that. Yeah. Yes. Stupid purple. Yeah. Okay. So again, you have this tower of covers where the first Betti number could be growing to infinity. Just it has to be very slow with respect to the degree or the index. Okay. So that is what we know. Okay, so that's great. So we sort of have a little bit of an understanding of what's happening to the first Betti number in towers of covers. So you could ask, okay, well, we understand this a little bit, or in some sense, what can we say about the torsion part? Can we say something in this sense? So here's the question. So what about torsion? Okay, and here is a theorem of Tangle. Sorry, I need to be like this. And he showed that if you have such a tower of cofinal tower of regular finite covers, then you can look at the lim sup of log of the size of this torsion group, T1 of Mn, over the index. And this is bounded above by, this is the simplicial volume of M over 6 pi. Okay? So here you should think of this as sum of volume of the hyperbolic pieces. Hyperbolic pieces. And this is just an upper bound. So in some sense, okay, so that's the upper bound. But let me also say that there is a conjecture. And this conjecture, I don't know exactly who to attribute it to, but I think there's versions of it that appear in Luke's papers or maybe his book. Also, Bergeron, Venkatesh, but maybe in more generality as well, and in this paper of Pangles, that says that there exists a tower such that, let's say, this limit is actually equal to volume over 6 pi. Okay? So this is just a conjecture, so we don't know. I think as far as I know, this conjecture is still open. Okay. And there is some numerical evidence for this conjecture. So I'll say that there is some numerical evidence for this conjecture, and I'll mention some names. There's some work of Nathan Dunfield, as well as Dunfield together with some of his collaborators, where they look at towers of covers, and I think sort of based on their numerical evidence, what one should expect is, at least in the arithmetic setting, if you want a tower where you achieve this bound, you might want to consider congruence towers, which we learned about this morning. So I won't tell you again what those are, but they come from reductions of modulo prime ideals. Okay. Okay. But I'll also say that it does seem, or at least based on their numerical evidence, that if you just take any tower, most likely you will get 0. But so you want something in particular to actually achieve this bound. But again, this is a conjecture, and I don't know how to answer it. So I'm instead going to answer, or I'm instead going to ask a simpler question. So if you want some sort of tower of covers to converge to this non-trivial number, then the minimum thing that you can ask for is that at least you have some torsion groups that are not trivial. Okay, so that's the question I'm going to focus on. So question. So here's given M as above, or I guess as what I just erased in the setting. Does there even exist a finite cover with T1 non-trivial? Okay. Okay. So I hope you can agree with me that this is sort of the easier question to go into. Okay. Any guesses on what the answer is? What? The answer is yes. So the answer is yes. And there is some history to this. So the first answer to this question was given by Hongbin Sun. And this is a paper that was published in 2015. And he showed that this is true in the case that M is a closed hyperbolic 3 manifold. Okay. And then more recently, in this more general setting, there was also some work of Friedel. I don't know how many n's. Maybe 2 n's. Maybe 1. I'm not sure. And independently by Liu, where they also answer yes to this question in the more general setting. Okay. But what I'll say is that Sun's result in the closed hyperbolic three-manifold setting is actually gives something more than just finding a cover with non-trivial torsion. So here, what he does is he does something that I'm going to call prescribed virtual torsion. Oh, I just realized I have another board here. I'm going to use this board. So I'm going to tell you the theorem now. Again, this is joint work with Daniel Groves. And this is given M. And again, this is M3, let's say compact, irreducible. With empty or toroidal boundary. And at least one hyperbolic piece. Okay. So given M like this, and also, let me say it like this. For any, if I take A to be any finite abelian group, any finite abelian group, then I can find for you a cover a finite cover where A is a direct summand in first homology of this cover. Okay? So this is the statement. So if I start with my three-manifold that looks like this, and you give me any finite abelian group, there is some finite cover that has that in its homology. Okay? So the way you should think about this is prescribed torsion, because I'm prescribing not just that the torsion here is non-trivial, and not just that it's as large as you want it to be, but I can find A as a direct summand. Any questions about the statement of the theorem?
Any control on the degree of your phase?
No. And you will see that, or we'll see that when I go through some of the ideas. I go into the proof. Okay. Maybe I'll say a couple words right now, is that we do go through the virtually special theorems. And as far as I know, we don't at the moment, we can't say too much about controlling that. Okay. Let me erase. Yeah. Yes. Yes, that was me.
So there are some cases where you change that entirely through the argument.
So in those cases, I can make the virtually special explicit, but there are other. I guess we refer to virtual theorems many times during the proof. So, no? Not at the moment, I guess. Okay. Okay. So let me go into some of the ideas that go into the proof. And the first thing is, how do you even construct a space that has whatever torsion you want in its homology? Okay. So how to prescribe, I guess this is the word that we're using, how to prescribe non-trivial torsion. Oh, there's a couple things that I want to say. Actually, I forgot to write this here. And I guess I said it out loud, but this generalizes Soon's work. And again, he did it in only the case for M, a closed hyperbolic three-manifold. Okay. So how do we prescribe non-trivial torsion? So here is, I guess, one way that we could do this. Here is a surface. Okay, here's a picture of a surface. And let's say I find in my surface some simple closed curve C. Was the purple better? Is this better? Okay. So let's say I find some simple closed curve in my surface that looks like this. So I can cut. This is what it looks like when I cut. And now I have two boundary components. Well, let's do orange. Are these colors good? Okay. So now I have the surface with two boundary components, and I can, let me say, for each of these, I am going to take the quotient that comes from rotation by 2 pi over n. Okay. So then let's just do it like this. I get some two-dimensional complex that I'm going to call xn. A2 complex. Okay, exercise. What is the first homology of this complex? Can anyone do it very quickly? Yeah, so let me write this here. So this is going to be C2G minus 1. Well, assuming this was surface of genus G. Okay. So as you can see, here's a way to give it this prescribed cyclic, finite cyclic group that we want. And if we did this along some other curve somewhere else, you can imagine doing this inductively to get whatever finite abelian group you might want. Okay? Okay. So this is...
What do you mean by you do back?
No. You just identify.
Each boundary.
Yes, on each one. Yeah. But this by the same amount. Okay. Okay. So now let me go over here. So let me give you, I guess, a quick overview of what was Hongbin's idea. And this is what we will be following again. is that you can find a way to immerse this particular two complex into a well, let me just say N here, because this is the case of the closed hyperbolic three manifold, but in such a way that the fundamental group of this three manifold retracts to the fundamental group of this complex. Okay, because then once you have this, then H1 of N looks like this. Plus something. Okay, so this is a general idea. We're going to construct a surface like this, but we have to make sure a lot of things work out to ensure in particular that we have this pi1 injective map and we have this retraction where this all works. And I'll say that Son, what he did, and he constructed this using Kahn-Markovich, which, as you might know, works only in the case that N is a hyperbolic three manifold that's closed. Okay? So you're not allowed to have cusps in here, and this is why Son's work does not apply in the general case that we're looking for. Canon right? Yes, that's what we will use, but note that that comes later. Yeah. Okay. Yeah. So let me go over here. I think I'm writing really big and having to erase a lot. Yeah, I guess writing too big is better than writing too small. So, okay. Oh, I need a color. I have colors. So, I guess this is the bulk of what goes into the proof. And what I'm going to do now is talk to you how we get around the closed hyperbolic three manifolds to do something similar. And again, once you have this retraction of the fundamental group level, you get the result that you want. Okay. Okay. So here's the idea of proof. And here I'm going to now assume that M is a finite volume hyperbolic three manifold. And let's just say that it has cusps, because otherwise we already have it from soon. Okay. Okay. And again, I'm going to do this by induction, so I'm just going to first fix N. Okay. Here's a picture. Let's say there's a couple of cusps here. Oh no. Okay, here's a little schematic of what my three manifold might look like. I feel like this looks like a stomach. Sorry about that. Okay. And here's what I'll say. So for large R and small epsilon, what I'm going to do is I'm going to find a curve, let's call it alpha naught, in my manifold such that the height, I haven't told you what this means, is at most log r, but you should think of this as far from any cusps. Far from cusps. And the complex length of this curve is, let's say, 2 epsilon over n is within of, let me see what my notes say. Okay, so I'll say that we are able to do this. We are able to find such a curve which stays some distance away from that, and I don't know, it looks something like this. It has some distance away from the cusps, and also we have a control on the length of the curve and the rotation. Okay, so this is a loxodromic coming from a loxodromic element, and we're controlling what the rotation looks like, and in such a way that if we take the nth power of it, this is what is called a good curve. Okay, and this is a good curve in the sense of Kahneman-Markovitch. Okay. Okay. So what we're going to use here is now, actually this was the first step. So let's do this here. Now step 2. Yeah.
About this rotation, you can't have if I don't know all the hyperbolic moments are hyperbolic.
If that was true, and if it was, you cannot have that for a finite volume hyperbolic three-manifold. So if you had something like that, I believe it would have to be of infinite volume. Yeah. Actually, it might have to be Fuchsian. Okay. Yeah. Okay, so that's the first thing we did. And now, as Julian kind of gave it away, we're going to use the new results of Kahn and Wright. And this is new. I'll mention here that this, or at least the preprint, came out in 2018. So as you can see, 2018 comes after 2015. So this was not available to Hongbin at the time that he did the closed case. But Kahn and Wright, what they did is they actually generalized Kahneman-Markovitch in the case that you might have cusps in your hyperbolic three-manifold. And as Julian also mentioned, there are some similar type results by Cooper and Footer. But I will say that Cooper and Footer's results don't really give you enough control on the constants that you see appearing, and we do need some control to make things happen the way that we want them to happen. Okay, so we use Kahn and Wright to construct a surface which immerses in my three-manifold, and such that a simple closed curve, let's call it C, in S maps to alpha. Okay. So I think you might get a sense of what we're going to do now. So the fact that this curve maps to alpha, and alpha was the nth power of this particular curve that we know a lot of things about, might help us know a lot of things. Okay. So here, and let me say, I should have said a lot of other words. Let's say this is almost, you said you can't see purple. No, you can't see purple. So this is almost Fuchsian, so we also here need some control on how close this embedding is to being, this immersion is to being Fuchsian. Okay. That's 2. Let's just go over here. Three. So the next thing that we want to do is that, I'm going to do this trick that I did over there. Use the trick above to now have an immersion of xn, this 2 complex, into M. But we want more things, and we want to ensure that it is pi1 injective at the minimum, but also we want a little bit more. Let me say this. And a fundamental group is a relatively quasi-convex subgroup of pi1 of M. Okay. And let me actually mention here that to get this step to work, we might need to go to a finite cover. Okay, so here is already one step where we are losing control on the degree of the cover. Yeah. Relative to the cusps group. Because in this case, we're not assuming that, that the fundamental group is hyperbolic. It's hyperbolic relative to the cusps. And in particular, because we're sort of finding this, we're choosing this curve to be far away from the cusps here. And in fact, we're actually also choosing to construct, I guess, immersed surface, which again is far away from the cusps. Okay. And there's a couple of reasons why we want to do this, but in the end, if we want to say something about more general 3 manifolds that have these as pieces, we want to stay away from the cusp so that we can glue other pieces to them and nothing goes wrong. Okay. So I will say that this is doable, but this is sort of the heart of the issue. So this is the hard part to do, is to ensure that all this works. Then we can go to 4, and here we can use the virtually special theorems, or I guess certain consequences of the virtually special theorems. And I guess in this case, I'm just writing the finite volume hyperbolic 3 manifolds, so I'll say AGO and Wise to find a finite cover and a retraction to the fundamental group of this space. Okay. Okay. Okay, let's say ... and then we have that C mod NC plus something is now the homology of this cover. Okay. So that's sort of the main idea of the proof. And again, like I said, you can sort of do induction if you want a higher ranked finite abelian group. And we made sure that we're staying far away to the cusp, so we can sort of glue on other geometric pieces to these cusps and go to the more general setting. Okay. Yeah. Okay. Let me also say, since it's still up there, this big conjecture about the growth of torsion, that as you can see, we have no control on the index. So this doesn't actually help at all with this conjecture. And also, these covers that we're going to are probably not regular. So again, it doesn't really help with the conjecture. Okay. So any other questions so far? Okay. Yeah, so that's sort of the main idea of the proof, but now I want to talk about a couple of applications to the arithmetic setting. So here is, I guess, sort of a consequence or a corollary. So now suppose that you have n, let's say, finite volume or arithmetic. Oh, again, this is real hyperbolic, a finite volume arithmetic manifold. Oh, and I also want to say here n is at least 3 of simplest type. I think after Tuesday, we should hopefully all know what it means to be of simplest type. Sometimes this is called type 1. Sometimes this is called standard type. So I'll say that here. But in this case, what this means is that these come from quadratic forms. And the fact that they come from quadratic forms, it also means that restrictions of these quadratic forms to complements of positive vectors give you restricted, they give you restricted quadratic forms that correspond to total geodesic submanifolds in here. So these are ones, I'll also say this over here. So these have immersed totally geodesic submanifolds. And in particular, because n is at least 3, they have some of dimension 3. Okay? And these also, plus type, also have prescribed virtual torsion. Okay? And again, what does that mean? Again, we can pick any finite abelian group and realize it as a direct summand in the homology of some finite cover of these manifolds. And this now holds for n at least 3. And actually, this is not just true of the ones of simplest type. You can also say it of hybrids or hybrids. Okay. And why is that true? Let me just say this here, that this uses the fact that these are still virtually special. And that was work of Bergeron, Hagel, and Weiss. And consequences of that in terms of virtual retractions due to Long and Reed. Okay, actually, I'll add some dates here. I think this is 2008, and I think this one's 2012. Okay. So in the last few minutes, I guess I just want to talk about now what happens in the case of complex hyperbolic manifolds and why this doesn't work. So what about this case? Let's say n at least 3. Okay. So if you had started with an arithmetic complex hyperbolic manifold of simplest type of complex dimension at least 3, then at least for some of them, there are easy ways to construct, let's say M is one of these. You can sometimes find totally geodesic, let's call this one N. Real hyperbolic submanifolds of half dimension. So let's denote it like this. Okay. So you might ask, can we do the same thing? So do, for example, this retract to this one, and then we can apply the same results that we did before. And what do you think the answer is? I already said it was bad news. So bad news. So these, I guess these lattices, I should have called them something. Let me do this. Oh, this one also needs a name. And unfortunately, lambda can never retract to gamma, okay? And this is bad news because this means that even though I can sort of construct these submanifolds in here, it's just not enough to be able to give us these results that we want. So I just want to end the talk, and I guess I'll end 5 minutes early, just saying that we don't know whether we can do this for complex hyperbolic manifolds, and maybe you should work on that, or we can work on it together. Okay. And I'll end there.